comes from the Greek word meaning putting together. Synthesis is a process of reasoning whereby we put disparate parts together to gain an understanding of the whole system. Synthesis may be contrasted with the opposite process of reasoning called analysis, in that analysis involves taking things apart to understand their components. Method used within a holistic paradigm. With synthesis, we understand something by looking at how the parts interrelate to form the whole, and how this whole system functions within its environment. Because the holistic paradigm always refers to the whole in order to understand the parts, synthesis reasons by looking at how the parts are put together to form the whole, and how the whole system interacts with other systems and operates within some environments. And this process of combining different things together to form a greater whole is called emergence. In the process of emergence, diverse elements interact, self-organize, and combine to give rise to some combined entity that exhibits novel and different properties when taken as a whole. Synthesis tries to understand this process of emergence and how the interactions between diverse parts can create something new. Synthesis then takes a holistic view, meaning it looks at the whole and is primarily interested in the overall workings. We regard a system as a whole unit when we treat it as a black box and look at its overall behavior and function, that is to say, what it does or accomplishes, instead of looking at the internal parts to see how it accomplishes it. For example, architecture is often considered a holistic discipline as it is primarily concerned with how the whole building works. Rather than prioritizing any single element to the building, the architect must look at how the parts interrelate to form the whole system. In contrast, building engineers are required for the analysis and design of the physical component parts to ensure that it will function. Synthetic thinking has three main steps that can be seen to be the opposite of analysis. To understand something using synthesis, one has to firstly ask, what is this a part of? Then identify the whole context that the system is a part of. For example, to understand a corporation, it is necessary to identify the economy. Secondly, we have to understand the behavior of the whole system. For example, one needs to gain a basic understanding of the transportation system and the economic system in order to understand the car and the corporation respectively. Finally, we have to identify the function of the system we're trying to explain and how it is interrelated to other systems in the performing of that function. For example, understand the role a car plays in the transportation system and the role a corporation plays in the economic system. Both analysis and synthesis provide very different insights. While analysis reveals the structure of a system and its internal workings, synthetic thinking reveals to us why it behaves the way it does. No amount of analysis to the French automobile would reveal why they drive on the right-hand side of the road. Why this happens is a historical, contingent part of the broader evolutionary context within which the car exists. Whereas an analytical inquiry may give us detailed insight into the workings of something, and thus an understanding of how it functions, it is also argued that reductionist approaches do not allow us to identify why behavior happens. Synthesis resolves this by referring to the broader context. Synthesis helps us to understand the meaning of something because the meaning of something is in its functioning within some larger system. A person finds meaning in their life by playing a part in some larger organization, a mother playing her role in a family, a person forming part of a sports team, or a musician in a band. It is only in reference to a system's functioning within a broader environment that we can derive answers to the question of why, and it is only really in taking things apart and analyzing them that we can get answers to the question of how. The effectiveness of either method is very much contingent on the context. Some phenomena and circumstances lend themselves well to analytical reductionism, others not so well. Which paradigm is most relevant may be understood to be contingent on the degree of complexity to the system we're dealing with. Simple systems are amenable to the reductionist analytical approach, while complex systems typically are not, due to their high level of interconnectivity and their interdependent nature. The basic word synthesis means putting things together to form some new entity. For example, in botany, plants perform the core function of photosynthesis, wherein they use the sunlight's energy as a catalyst to make an organic molecule from a simple carbon molecule. Thus, synthesis is essentially a creative process. Synthetic thinking is designed to create new, out-of-the-box ideas and solutions. Whereas analysis can't really tell us anything fundamentally new, it gives us incremental improvements and optimization. Because we're simply breaking things down, it can only build upon what already exists, while synthetic thinking can enable major paradigm shifts due to its creative, emergent nature. While analysis gives us differentiation, which is important to achieving efficiency through specialization. However, it can lead to fragmentation over time. Synthesis puts things together, thus it plays an important role in systems integration, making sure that all the parts are working together in an integrated fashion and that things do not become too fragmented. Thinking can be an important element within a system to ensure its alignment with its overall environment and long-term sustainability. A corollary to this is that because everything is seen as context-dependent, holistic systems are optimized for adaptation and responding to change within their environments. Whereas an analytical paradigm leads to the idea of determinism and predictability because the focus is on the internal workings of a closed system. That is to say, everything that will exist already existed in the past and is determined by that. Synthetic approaches hold that the behavior of a system cannot be perfectly predicted no matter how much data is available. Nature and social systems can produce surprisingly unexpected behavior, and it is suspected that the behavior of such systems may be computationally irreducible, which means it would not be possible to even approximate the system's state without a full simulation of all the events occurring within it. In the face of this uncertainty, adaptive capacity is seen as having great value within the holistic paradigm. Both synthesis and analysis are central to gaining a full understanding of any entity. Both have their achievements and limitations, and both are required for a full, balanced understanding of the whole and its parts.